Instead, you can also just take many wires together, and if you put them close enough together such that this evanescent mode of the wire starts to overlap with its neighbors, what you actually can see is that if you inject light into the one of those waveguides, it will start actually hopping to its neighbors as it propagates along the z direction. So if you write down the equation now of how light evolves in these coupled waveguide arrays, you actually find a differential equation that is exactly the Schrödinger equation for a discrete system. So it's on the right-hand side, you see a tight binding type Hamiltonian. But now instead of time evolution, you see Z evolution. So this is then allowing us to have a spatial modulation of time. And this is a highly tunable platform that allows you to play around with tight binding models. So, for example, you can take various waveguides with various refractive indices, and you can then modulate the on-site potential of your simulated model, or you can then change the inter-waveguide distances, and by this modulate the hopping between your waveguides. Usually, there are two leading technologies that people are using to generate these optical waveguides. One of them is semiconductor lithography methods. You can either do masks or etching, where, for example, here the upper cladding is modulating the refractive index in this core layer. Or you can do what is known as a femtosecond etching technique, where you're actually taking bulk glass, silica, and using a highly focused, high-intensity laser beam, you're actually burning structures inside this glass, and this burn is going to have a different refractive index and will serve as our waveguide. So we're talking about topology. Topology is usually done with electrons, and electrons fill up to some chemical potentials, or probably yesterday you've heard of atomic systems where you cool down to the ground state and you feel some ground band of the system. In these photonic waveguide arrays, we don't have this energy resolution. The only thing that we have is the ability to pick an input port or shape the input axis, and then the input state is going to overlap now with all of the eigenstates of this structure, and will then evolve in time, or respectively in the z direction, up until a cut point, which is controlled by the length of the specific chip, where you can then image the output intensity. So in this sense, we don't have a notion of filling up a band and seeing some quantized bulk response, as we are used to in thinking of electronic topological systems. But this is quite a neat tool to then selectively address boundary phenomena. So just to give a short reminder of why we want to see boundary phenomena in topology, let me just remind you the general bulk boundary idea, that if I have a topological system, say, on the left-hand side, and it has, say, two bands with some topological indices, nu1 and nu2, because these are integer indices, if I have an adiabatic modulation of my model, they cannot change continuously because they are integer. If I then use this adiabatic modulation to reach to another model that has different topological indices on the right-hand side, something bad must happen. Something in my ansatz must break, and this then will yield to a topological phase transition. So that was the onset of why topology is actually interesting from a condensed matter point of view. We have new type of order parameters that induce phase transitions. So I can repeat this argument, and now I can do my adiabatic modulation in space, and something along the way must break. And now I will have on the left and right-hand side some two bulk materials, each with its own topology. And on the boundary between these, I will have the manifestation of the topological phase transition in the form of some sub-gap modes that realize this phase transition. So with the photonic waveguide arrays, these modes are exactly the ones that we are hunting for, and I will just now give you examples of various techniques in photonic waveguide arrays that we used in order to image these boundary phenomena. So first thing, we can just inject light at the boundary. And probably the most known optics result is actually without me, by Michael Rechtsman and collaborators, where they have taken a hexagonal waveguide structure. And this hexagonal waveguide structure will have a characteristic graphene-like Dirac cones at 6 points. But now you can actually shake this structure. But instead of shaking in time, you can shake it in the z-axis. And realized a proposal that was proposed how to realize by circularly polarized light on graphene a Hall-like effect. So this is then nowadays more commonly known as the Floquet topological insulator. So by shaking, and here you're just, they call it Fusili waveguides, you're breaking the Z translation. If you inject in from this axis or from the other axis, you're opening up a bulk band gap, and you're seeing this characteristic non-reflecting chiral edge modes. And in the experiment, what they can then do is, due to this control that they can just choose in where they are exciting their sample, they could inject light at the boundary. It now mostly overlaps with these chiral modes because they have the biggest weight at the boundary. And what you see is that actually then light starts to propagate along the edge. And what optics people really like about this is that light can now actually go around corners and not deflect. Okay, so this is then a source for various ideas for applications. In atoms, these realizations of Floquet topological insulators were also done, and you can see the fuzzy references over here. So Uli introduced yesterday quasi-periodic models, and we were interested in the topology of quasi-periodic models. So we wanted to then also image bulk topological transitions between different types of quasi-periodic models. So in order to do that, using coupled waveguide arrays, we could really just repeat this argument that I showed you before, where we would have a bulk model with a given modulation, quasi-periodic modulation frequency, and then a smooth boundary that goes to a completely different one. And then you start to see, as the boundary gets to be longer and longer, you start to see this closing of the band gaps. And this is then also easily imaged using the photonic waveguide arrays. Now I don't want to inject at the boundary, but I want to inject actually at the interface and see evidence of this bulk topological phase transition. So this is just an example of an output light intensity distribution that you can see on the other side of the array. And you can inject at actually each of the input parts and get a completely different light distribution. And you can then quantify this using some return probability. And you can then see that in the bulk, the light gets to be quite extended. And you see then evidence of these localized modes that exist inside this band gap. So that's it for linear waveguides, or for waveguides that can then do something which is like a Floquet type shaking. Now, what we can also do is we can make adiabatic slow deformation of the waveguides along the z direction. So by this, we can realize topological pumps. And what you see here is the off-diagonal Harper model, where you have modulated hopping with this cosine potential. And effectively, what happens is that as a function of this additional parameter phi, I will just have every time a different inter-waveguide distances or inter-atomic distance. If I'm drawing the spectrum of this model as a function of this parameter phi, you're seeing that I have bulk bands and some sub-gap modes that are crossing the gap as a function of this parameter phi. So this is not surprising. This is because this model realizes something which is known as a topological pump. And if you're doing a process which we dubbed dimensional extension, you can actually extend this whole family of one-dimensional models plus a parameter and find out that it maps into the two-dimensional quantum Hall effect on a lattice. So in this sense, it's actually a variant of the Hofstadter model that you saw yesterday. So these, in the 2D language, these will be chiral edge modes. In the 1D boundary, you might sometimes have such a boundary mode, or sometimes not. The bulk boundary correspondence of the topological pump just guarantees that it must appear along this scan of phi from 0 to 2 pi. So with this in mind, we then went and realized the photonic waveguide array, where the inter-waveguide distances are now slowly modulated along the z-axis in order to realize every time a different snapshot of different phis here along the way. So if we take this cut as a starting point and inject light on the right-hand side, we see that we will mostly have spatial overlap with these two localized modes. And as light will evolve along the way, it could be that you will not have any localized mode on the boundary at all. And if you continue, you can actually find out that you can have adiabatic pumping of light from the right-hand side of the sample to the left-hand side. So this is an illustration, but these are actually the experimental results, where there we did not have fluorescent techniques that I will show you later, but we actually had to have 75 layers of different propagation lengths in order to see how you see pumping of these edge modes under the hood, quote unquote. We could then, additionally, in the same spirit of pumping, make a mapping between Harper-like model and Fibonacci-like model, and realize a similar pumping for the Fibonacci quasi-crystal by using our deformation, and then pumping it to the right-hand side, and this is, again, the experimental results of how a Fibonacci pump looks like. Atomic pumps were also then realized, and you can see their bulk responses in these two works over there. Moving beyond one-dimensional arrays of pumps, we then looked at the two-dimensional pump, which then corresponds to two types of these off-diagonal Harper models in each of these directions. And what is nice about this model is that actually if you do dimensional extension for it, you see that it maps directly onto the four-dimensional quantum Hall effect that Hannah told you about yesterday. So if you then look at its spectrum, the spectrum of this model as a function of these parameters, you will start to see that it's a huge mess. We have something that looks like bulk bands that are crossing the gaps, and some additional corner modes that are crossing over here. But all of these can actually be mapped as a corresponding bulk boundary phenomena to the family of quantized responses of the four-dimensional quantum Hall effect. And then you can image these responses as well. So in fact, you can create such an array. This was done with Michael Rechtsman. And see that you can either pump from one side to the other something that looks like an edge mode, or you can additionally pump across the sample diagonally a corner mode. And if you want, I can explain to you why this illustrates the boundary correspondence with the 4D Hall. So I'm running out of time. We also realized the bulk responses of these such a 2D pump in a cold atomic system. This was done also with Hannah, which is here. And I will just give you last sample of what additionally can be done. If you etch these modes with a rich hydroxide system, you are starting to generate whole carriers along the waveguides, and you can actually image the whole light propagation as you excite it then. So you can actually now look on top and see the whole time evolution as it goes. So using an array that looks like this, that you actually have waveguides, normal waveguides, but an additional waveguide along this edge that is strongly detuned. It has a strongly different refractive index. So by doing this control, you can actually effectively see that light just mostly hops between these two waveguides with the same amplitude as before, with slight leakage into this additional auxiliary waveguide. But officially what you generated by this is a flip of the sign of your hop. So now if you embed such an edge inside a square like this, you can simulate a synthetic gauge field, a pi flux through this cage, and this is called an Aharonov-Bohm cage, and now light destructively interferes and doesn't want to propagate, so you're generating flat bulk bands. What you additionally see is that such a model has subgap modes fixed to square root 2 of energy. So using the same imaging techniques that I told you, you can actually excite in the bulk, excite on the edge. You see actually that light is mostly localized because the bulk bands are flat. But what is important is that now using this fluorescent technique is what you can actually see is the beating frequency along the bulk and the beating frequency along the edge. And you can actually see that the beating frequency here is faster because the bulk bands that you excited, which are these upper, blue and upper and lower ones, have a larger energy difference. So it has a faster beating coming from this type of evolution than what would happen when you excite only the boundary mode. So by this, you can actually also do spectroscopy. You can see the energy of the modes that you excite and not only excite something by its position. Last comment. You can also take this off-diagonal Harper model, and now you can, instead of injecting classical light, you can inject single photons into them, and engineering an array that has subgap modes that follow this type of evolution as a function of Z. What you can actually generate is that you will have localized boundary modes on the edges that get to be focused again in the center and defocused again to the ends. So you can have on-chip topological beam splitter or Hongo-Mondel interferometer. So you really tune it like this that if you shine in a photon from this point, it will just split to these two branches after this modulation. And this topological boundary mode will split into these two directions. And these are already the experimental results, by the way. So a single photon truly just splits. But when you're then shining two photons at the same time, and you're counting the coincidence of these photons to appear on two ends of the sample, what you actually see is a dip, which shows to you that these two topological boundary modes are actually showing also a two-photon interference, and the photons bunch along this modulation. So this gives hope for also using on-chip topological quantum technologies. So with this, I would like to thank my collaborators on these activities, and thank you for your attention.